Hello everyone. Today I will be presenting the LED matrix experiment, and in this experiment I have an innovation in which rather than displaying a character I will be displaying the shape heart. So this experiment demonstrates how we interface an 8 into 8 LED matrix with an 8085 microprocessor kit using 8255 programmable peripheral interference. We use a technique called column scan multiplexing to display a heart pattern efficiently on the LED matrix using software control. Let's begin with the module overview. The LED matrix consists of 64 LEDs arranged in an 8x8 grid. These LEDs are controlled using the 8255 PPI, where port A controls the rows and port B controls the column. The system uses multiplexing, where columns are activated one at a time using a rotated zero pattern. The logic is simple. When a row is set to logic 1 and a column is set to logic 0, the corresponding LED glows. This allows you to control multiple LEDs efficiently with a limited hardware. So now we will look how a heart can be represented using a LED matrix. So the heart pattern is defined as a pixel map where each row corresponds to an 8-bit binary value. These binary values are stored as hexadecimal codes at corresponding memory locations. So each one represents an LED that should glow and each zero represents an LED that remains off. This pattern forms the visual shape of a heart. In the right table, we can see that row 0 is 66 hexadecimal, row 1 is FFH, row 2 is FFH, row 3 is 7EH, row 4 is 3CH, row 5 is 18H, and row 6 and row 7 are not glowing at all. Next is the 8085 assembly program used to display the heart. First, we initialize the 8255 control register to configure all ports as output. Then, we load the address of the heart data table, set a loop to scan all 8 rows, initialize the column pattern starting with FEH, and then inside the scan loop, what we do is row data is sent to port A, column data is sent to port B. The RLC instruction rotates the bit, activating the next column. A small delay is added to make the display visible. This process repeats continuously, creating a stable image. This slide shows the memory representation of the heart pattern. The data is stored starting at memory location 2050H. Each row's binary pattern is stored as a hexadecimal value. For example, 66H corresponds to a first row pattern, FFH represents a fully lit row, 00H represents no LEDs lit. Important note, rows are connected to anodes, columns are connected to cathodes. So an LED glows when row is equal to 1 and column is equal to 0. Now let's go through the experimental setup. So we first connect the LED matrix module to the 8255 interface using a 26-pin FRC cable. Then we enter the assembly program into memory starting at address 2000H. We enter the heart pattern data at address 2050H and then we execute the program. Once the program runs, the heart pattern will be continuously displayed on the LED matrix. So now let us see how column multiplexing works. Only one column is activated at a time. So step 1, C0 active, step 2, C1 active, step 3, C2 active, and step 4, C3 active. This continues for all 8 columns. The RLC instruction rotates the 0 bit, shifting the active column. Since this switching happens very fast, the human eye perceives it as a continuous and stable image. This phenomena is nothing but persistence of vision. So to summarize, we used an 8 into 8 LED matrix, which have 64 LEDs in total. We control it using the 8255 PPI, implemented column multiplexing for efficient display, used heart pattern data, the RLC instruction helped rotate the active column, and finally persistence of vision method made the image appear steady. So this experiment demonstrates how hardware and software work together create a visual output. Thank you. And now in the next slide, I will show you the proof of execution, which demonstrate that I completed the experiment successfully.